inviting me to speak here. So we have heard a few interesting papers this morning, and I would like to try to put them in a perspective. So here is what is going on in analog design, just to recap the entire analog design process. In modern technology nodes, analog designers are not the ones that get to pick their technology. It is technology that fits the best the big SoC that is in some of these single-digit nodes. So some things that are relevant to analog designers are picked from there, like minimum channel lengths and what are possible FTs for that particular process, and metal structure that comes with that package. Then the human designers set the specs for the product for a particular analog interface. Say if it is an A to D converter, they need to choose signal to noise and distortion ratio, SFPR, bandwidth, and so on, and similar kind of parameters for, say, some kind of a high-speed serial. Then the analog designer, block analog designer, steps in and derives the parameters for that block from the overall specs for the analog subsystem. So for example, if it is some kind of a pipeline analog to digital converter, they would be picking the gain, the bandwidth, the settling time, input range, output range, and then deriving capacitances and so on that are needed to achieve the desired performance. In the process of doing that, they will start building a test bench that is an ongoing process, and relatively early in the design, they should start building behavioral models for integration, because it will be integrated in a bigger system. Then they start iterating through a process of schematic sizing for that block. Say if it is an op-amp, they need to pick the sizes of all the transistors and capacitors, as we have capacitor resistors and bias points and so on that have been mentioned earlier today, and refine it in the process of running simulations by updating the test bench and going back to the layout and fixing things there. Then, after the specs are met, that needs to be integrated, and that changes things often because things might not have been envisioned early on. How are they going to fit in the final design? And they continue iterating through that process. That is often a pretty lengthy loop to close the design. So here is some metric of how approximately, maybe a little bit cartooned, how long do these things take, and this, the size of rectangles indicates approximately how long does it each step take. So design specs are relatively early picked on. Then from there, test benches, initial test benches are relatively quickly put together. Schematic sizing is also a relatively quick process. Nowadays that a designer comes up with an initial design based on what they've learned in school or what they've practiced for a while. But then comes a simulation, and often these simulations could be lengthy. Building and refining the test bench and simply running them. Depending on whether the specs are met, they go back to the previous step. But when they need that, they go to a much bigger step, which is generating a layout. This layout generation is typically a manual process. It takes significantly longer time than just sizing a schematic. And then they may notice some, in the process they need to write event-driven behavioral model that is going to be used for integration. That does take a while, and it typically is integrated over. Then they need to produce SoC integration collaterals, also multiple steps here, indicated as one big block. And these kind of things, as the SoC integration issues are resolved, typically involve multiple iterations through the process. Okay, so let's go to some of the early steps. What is this analog sizing process? We've heard quite a bit about that. So it follows a design procedure that has been outlined many years ago, I think. Many people will point to Graham Meyer's tutorial paper from 1974, how to size and how to design a two-stage op-amp. More recently, people typically follow GM over ID methodology, as outlined really well in this Sanson's article in Solid State Circuits magazine in 2015. Basically, there are two main inputs into the process. Specifications say for a design that can be simplified to gain bandwidth and capacitive loading, and technology selection that, as we have mentioned, sets L-min and FT. And then, by following this procedure, I'm not going to drive through it in detail. The designer picks this inversion coefficient, or what is in old terms, if you're still using quadratic models, it is what is the overdrive of the transistors. And, in older classes, what we have learned, set an overdrive of about 200 millivolts on MOS transistors. The best results nowadays are somewhere like 35 to 50 millivolts. That number also, depends on the linearity requirements and so on. And that comes from graphs like these that are shown on the right-hand side. The design basically puts into two choices in there, that inversion coefficient, or somewhat related to the overdrive voltage, and the channeling that they want for their design, whether it, what multiple of a minimum channeling they would like to have for their analog design. And everything else falls out straight from that. And take a look at the very basic example of a common source amplifier. The gain is very well defined. It is GM RDS. Bandwidth is set by the RDS and capacitive loading. Gain bandwidth is something that, really what the designer has. A choice there is GM. Everything else is set for them. And there is a figure of merit that lots of people tend to compare their amplifiers against each other. So if something has a dominant pole, that is gain bandwidth times the capacitive loading, and that dominant pole with the output divided by how much current does it draw. All right. And these numbers, if you look at Sanson's numbers, depending on where you are on this plot, all right, it shows up over there. It can be 1600 megahertz picofarad milliamps with about 200 millivolts overdrives, or twice that much if you go down to 35 millivolts, around 65 nanometer nodes. Okay, so this is a heuristic that every analog designer, when they enter the field, typically knows how to do. Sanson advertises this op-amp design in a day. Typically, this process takes a lot shorter. Now, but there are a few complications. Layout parasitics come into the play. They can be predicted to some extent. Generally, designers will add some layout parasitics to their design as a linear penalty to everything, so 30%. And that sometimes works. If there's something simple as a common source amplifier, that'll work. They just include that, and there is not much action happening. It is a well-behaved design, it'll work. But often, layout iterations are going to mess that up. So, coming up with a real impact of layout parasitics, is a lengthy process. It will change the performance by more than a few percent that we can optimize things to just based on schematic. There has been a trend in academic community to build relatively complex parasitics models, and people in the industry have done that. They do have models for a particular process that try to stretch over multiple designs, but that's really difficult to maintain. It's a very domain specific. So the solutions to try to accelerate layout generation are through layout generators, or perhaps automatic analog layout. Layout generators is what we have been using for a long time now, and a lot of our designs are based on analog generators. Automatic analog layout basically gives a schematic to a tool, and tool lays it out. There have been some successes, but really for medium performance blocks. Okay, I mentioned analog generators, we use something that is called the Berkley analog generator, which is an open source hierarchical Python framework that embeds this design procedure. And it works extremely well, especially in small nodes when we run into FinFETs and the situations where there are many more infeasible designs or incorrect designs than the ones that are actually correct. If you look at what does the Berkley analog generator encompass, it has a schematic layout generator, or schematic generator is really not that big of a deal. Layout generator is a big deal there. It has a measurement manager that helps with some amount of automation of measurements that need to be performed on that design, and the design script that is manually manually coded up. Either equation, early on it was an equation-based design script, or a tabulated search through the widths and lengths. Well, that is an obvious place where ML can be plugged in, where an ML agent can be plugged in. So let's take a look at very quickly how does an analog generator work. So here is an illustration of how we built this really simple common source amplifier that I mentioned in Berkley analog generator. So it starts with a floor plan, or you can view it as a sticks diagram, and everything is parameterized. The number of pins, the number of metal tracks, the number of fingers, and so on. So what the designer would do, walking through this process, would start with defining the basic grid that will be underneath. So it defines the fins and the gates and the metal tracks. Then defines the transistors, where will be the transistors in the intersections of these polygons, or both N and P. Then would add the gate contacts for the inputs, add the drain contacts for the outputs for the load, and the bias gate contacts on top. Would move on to the next step, add the wall taps, and then add VDD and grounds. Each one of these steps is, as you can see, 3 or 4 lines of Python code. All of this nicely appears in the layout over there, and finally finalize the design by defining the pins and labeling the ports. Okay, so here is something that we can do. The topic of today is, where does the ML play a role? So, as we have seen already, there is a lot of interest in having ML as some kind of a designer's aid, where they would help with transistor sizing. So the way how it works is we have a number of parameters to tune in a circuit, say widths and lengths, or just the widths. You could pick some particular length that we care about. And then we have a number of design specs that we would like to do. And then we would like to search the parameter space that we will typically discretize. Discretize widths and lengths because they have to be discretized in these modern processes, and try to meet the circuit, evaluate the circuit performance such that it meets these specs with a minimum of power. It is typically set for every design. It is set as an optimization problem, so we try to find the parameter vector that meets the spec for minimum power. Now, one of the catches there is almost no open source training data except for textbook examples. So the data needs to be generated on the fly. That's why we have seen so many attempts now to go for reinforcement learning. But reinforcement learning is not the first entry at this point. Back in late 80s and early 90s, there were quite a few attempts at building these knowledge-based systems that were partially equation-based, partially heuristics, and quite a few well-known people from the CAD community have put their effort in there, or put their mark in it. With every new wave of optimization, there was a new wave of optimization algorithms. There was a new attempt to try to do this in the analog design. Well-known one was in late 90s, the work on geometric programming that resulted in a few companies that followed that. And then advancements of genetic algorithms also revived some of this thinking a few years ago. Now, all of the effort is in reinforcement learning, and we have seen this before. I don't need to too much dabble into that, but essentially, the agent observes an environment, it provides some actions, and then based on observations and rewards, directs this design to explore different thoughts. We built one of these things, probably one of the early ones, which was called OptiCircuit, and some people have mentioned hardly today. It's a simulation in a loop-based algorithm that essentially took the netlist, first just a schematic netlist, then later coupled to BAG, with an agent which was a gem from OpenAI, and manipulated it. It worked fairly well. It took a while to get this to behave and to work in such a space, but the results were pretty promising. So when we work just on the schematic, two-stage op-amp is something that we know the solution for, so we better match the human, or if it falls behind the human, then we have a problem. We have a clear benchmark of what we're doing. If it outperforms the human, it usually, every time it outperformed the human, it meant that we did not set some spec correctly, for some constraints correctly. So it's in the end, the good news, RL agent matched the manual design procedure perfectly. But it required about 10,000 iterations to do that. Searching this fairly large space of the order of 10 to the 10. And if each iteration takes from a fraction of a second, depending on what it is, to tenths of seconds, where that may be in FinFET processes, well, this is about 10,000 times slower than a human doing this. So really, no point of doing these things for schematics, unless it's a schematic that we don't know accuracy for doing. So the next step is, let's try to couple this to BAG and couple it to a generator. Generator is now this digitized form that we can manipulate and actually run actual extracted parasitic simulations. So that work, that took quite a bit of an effort. Conceptually, it's the same thing. We are just extracting a netlist from BAG. It just has parasitics and annotated to it. But a lot of plumbing there went through these obscured APIs that exist in commercial tools. So that took quite a bit, but in the end that worked. Some of the things that you have noticed here is that each simulation step takes about 5 minutes now. And that becomes pretty long when we need to run through tens of thousands of these. That's gonna time out pretty quickly. So the way how to do that, you mix, you run some number of schematic-only simulations and then learn some of that learnings to parasitic simulations, and only once in a while you run some parasitic simulations, maybe every 10 simulation there guides towards. It has to be done with the actually back-end parasitics. And that worked. It does take some heuristics and some tuning to figure out how, what's the right mix and how things work. But intuition there is similar to this, robot learning on the flat ground versus on the rough surface. Then the ideas there essentially come from our attempts to search the space where most of the design points are. Now, this was tested on a two-stage folded cascade op-amp design. So now, if you include the bias network, we have 44 parameters. It is done in TSMC 16 nanometer process. So the design space here is 10 to the 44 because each width was quantified 1 times to 10. It was coupled to a layout, and it produced a layout now that what we see here, when we set the dominant pole at the output by having a high load at the output of about 1 picofarad, it matches a human designer. Actually, it outperformed the human designer, but human designer looked at this and quickly corrected their design, and it was, we all agreed that this is optimal. Both agent as an aid to a designer, and the designer said, "Well, this is as good as we can do." But there are some other interesting experiments that we fed to it. So here is a design that did not have a dominant pole, so parasitics mattered a lot more because the spacing between the dominant pole, the pole at the output, and the pole that was inside the amplifier was about an octave. So parasitics on that internal pole mattered, and the phase margin was changing widely. So what you see here from a lot of these plots, here is a phase margin based on schematic only versus a layout. So although the schematic only, we thought we had a whole bunch of dozens of good designs. If you look over here, post layout, there are like only 3 good designs in the upper corner. So that is something that is important to remember. Now the point here is AutoCircuit made some good progress. It got some automation going, and even more important than that, we got some confidence that it matches a human. And that's good. We did not expect to outperform human. We matched the human, and we understood what it can do. Training, that did take about the same time as final design, which is weeks once when we get the specs right. But deployment is fast. So if somebody starts building databases of these op-amps, then it can go relatively quickly. But there is something also interesting. We could size a circuit where a designer would typically give up. They would not generate all these layouts that you have seen in the previous slide, where the specs are wrong. So it did it. Although a designer would more likely pick a different topology and solve it more cleverly. We can't do that in BAG because we will need a generator for each topology. It would take us a while to get to. Maybe if somebody wants to invest into something like that, or try to build some kind of analog design automation. So perhaps one of the possible next frontiers is to try to move topologies. And if you look at these 2 designs that are on the bottom, one, they're almost the same op-amps. One of them has just capacitive compensation, the other one has DRC compensation to cancel the 0. This is something that is typically taught in classes, but topologically they're different. There are 2 different netlists. 2 different graphs correspond to these two different circuits. I mean, you can still represent them in the same graph. You would have to have some kind of an impedance matched over there, but it is nominally a different topology. Our optimization will fail on this. We need to learn on one of them, and if we want to change the topology, we need to transfer that to a different graph. There is some work. There is a paper here that just got published recently on Archive, where there was this automated topology transfer, where it's quite a bit of learning done, because there are so many, there are very few value points, so you can get many, a lot of notion of bad designs just from these simulation points. You can give up, we can toss 99.99% of the designs out of that, and then transfer only good stuff over to the topology. Few other things that I would like to mention here again. We know that this is what we did so far. We got this loop kind of working. But there are other things that are out there. We need to write event-driven behavioral models. And BAG 3 does help now with that, but it would be great to have a little more of this designer intent in there. Produce SOC integration collaterals. Well, there is an API now that exists from BAG into Virtuoso that will do that, but it needs more integration with other tools. And then, there are SOC integration issues. Bag 3, all the other experiments were done in Bag 2. Bag 3 does now have a C++ layout engine, however, it is not an open one because it is obscured behind proprietary APIs. So it's very difficult now to couple in an ML engine to it. So there is stuff that can be done and things can work much better. So RL agents can optimally size analog blocks and generate layout. Challenge here, computationally, this is limited to about 50 parameters or so of practical training time. Maybe a little bit more if we try to deploy a little more fancy RL techniques. But we are talking about exponential. 10 to the 50th is a very big number, even if we shave off 30% of it. Ideally, we would like to have a framework that would mimic a designer, that would pick topologies, size the design, and generate layout, write the test bench, produce behavioral models, and resolve integration issues. And preferably be composable and scalable such that we just don't have to design op-amps, but we can design complete serial links automatically. Or at least help a designer design them semi-automatically. I believe that open source design kits are an enormous opportunity. We can run screensavers with them, perhaps. Or even better, we can perhaps run design contests. There is one challenge. The models are just not usable at the moment. Whatever has been open sourced just does not make any sense. So we need to create some incentives to get reasonable models, reasonable open source models, and perhaps people to open source their designs now, since the models are there. With that, that's all. I would like to thank various people who have been sponsoring various videos of this work. Thank you.